And section 10.1 is going to all be about circles, specifically lines and segments that intersect circles. And I don't want to write that all out right now as a title, so why don't we just get started with saying circles and such. So it would be nice to know what a circle is, right? We can all define a circle by drawing one, right? If my software works there, we got a circle, right? A perfect circle. And this circle, like all circles, is going to have a center, and we can name that center P. All right, so this would either be called circle P, or you can name it like this. So draw like a little circle, put a dot in the middle of it, call it P. That it identifies that this is circle P, and P is the center of that circle. So a circle is the set of all points in a plane that are equidistant from a given point called the center. And so we have a couple of key terms here. First off, we need to know what a circle is. Second, we have to remember what equidistant means. Equidistant means that every point on this circle is the same distance from P. So those two yellow lines going out to the arc of that circle are equidistant. Those are called the radius. We'll talk about that here directly. And this center point, P, is called the center. All right, and we would label our circle like this, circle P or circle P. So now that we know what a circle is, just as a quick reminder, why don't we go and talk about some of the more nuanced facts about circle, and specifically lines and segments that intersect circles. All right, so why don't we get started by just drawing a circle, and we're going to call this circle P. And we're going to draw everything as we move along here. So why don't we get started with a term that I already threw out, the radius. So this red line right there, that's going to be our radius. And there's infinitely many radii on a circle. And so a segment whose endpoint, or endpoints I should say, are the center of the circle and the edge is a radius. All right, most of you guys probably already know what the term radius is. And likewise, if we go the full distance across the circle, so we go from edge to edge, cut that circle in half, that blue line is going to be called a diameter. So a diameter is a segment that goes from edge to edge and through the center. So we have these two lines here, these two segments, one goes from edge to center, and the other one goes from edge to edge, but also goes through the center of the circle. What if we draw a segment now that goes from an edge to an edge, but doesn't go through the center of a circle? And this segment is going to be called a chord. And so a chord is a segment whose endpoints are on the edge of the circle. And because of that information, you know that a diameter is also a chord. All right, we're running around out of room here on this first circle, so why don't we draw another circle? That's definitely not a circle. There we go. Here's another circle. It doesn't matter what we call this one, so we could call this circle Q. And we're going to define two final words. The first one being secant. A secant is a line that intersects a circle at exactly 2 points. So it's just like a chord, except now instead of being a segment, we have a line. So this yellow line right here would be a secant. And then finally, we're going to end off with what is called a tangent line. And a tangent line is also a line that intersects the circle at exactly 1 point. And that point is the point of tangency. And so if you want to draw a line that intersects a circle at 1 point, it's going to look kind of like that. So imagine my black circle here is like the wheel of a tire, and the purple line down here is the road. And so when your tire hits the road, it's only touching at that 1 point, right? And this purple line is going to be a tangent line. And it's going to intersect here at exactly 1 point. We're going to call that point B. And that is going to be our point of tangency. All right, so I'm going to move on. If you want to pause the video real quick and write down all these terms, make sure you have them, that's fine. But I'm going to go ahead and move right along because there's still quite a bit of material to go through today. So just so we have the gist of everything that's going on, I'm going to draw another circle here. Everything's going to be in black to make it a little bit more hard to visualize. And I want to just see if we can identify some of our different lines here. All right, so we have a circle, we have two lines and a segment on this circle, and let's see if we can identify some different things. We're going to first identify what is the line or the line segment, I should say, AC. And so if we go and find AC right here, here is A, and it goes to C. And so that, going from the center to the edge, is going to be a radius. Next, why don't we take a look at the segment AB. Once again, we'll go ahead and look where AB is. So here is A, it goes out to B. So that segment would be the diameter. It goes from edge to edge, but also goes through that center point there. Just realized we created a really ugly color right there. Oh well, let's move on. Next, why don't we take a look at the ray DE. So we got to find where D is, and we're going to go out to E. This is going to be a ray. So we're going to start right here, go down to E. We're going to continue to go because it's a ray. So notice that it's going to intersect exactly here at one point. So that is a tangent. All right, but specifically, we're going to call it a tangent ray. And then finally, we're going to look at line AG. So we're going to find where A is, go out to G. It's a line, so we're going to go off indefinitely on both sides. It intersects a circle at 2 points, and exactly 2 points, so that is called a secant. So now that we've identified some lines in our circle, why don't we go ahead and take a look at some different types of circles you might see. So let's talk about coplanar and coplanar circles and common tangents. So circles can intersect pretty strangely. All right, so let's first take a look at the different types of ways circles can intersect. So if I draw a circle here, come on, make a circle. Do your circle thing. Okay, it's not going to make a circle, but that makes a circle. Okay, so we got a circle there. We got a circle here. Notice that these two circles intersect at exactly 2 points right here. So when this happens, we're going to call that a 2-point intersection. And just like how this would be a secant if we were to draw this ray from here to here, or a chord, I should say. If it was a line that kept going, that would be a secant. We could have circles intersect at exactly 1 point, and those are going to be called tangent circles. And those can look 2 different ways. We could draw a circle like this, and then another one inside. That is not what I wanted. And they can intersect right there at exactly 1 point. And then we can imagine a tangent line going through that point, like so. Now let me redraw that tangent point. So there's our tangent line right there. Or we can have tangent circles that are on the outside of one another and touch at 1 point, like so. And once again, it wouldn't be too hard to imagine our tangent point right there and our tangent line running down the center of those two. And so if we have circles that have 1 point of intersection, those are going to be called tangent circles. Whoops, didn't mean to go all wild there. And then finally, we can have no points of intersection. So that's just going to be two circles that don't intersect each other. So these two circles right there, those have no point of intersection. And if you're pretty good with geometric shapes, you could also probably identify that there's another set of circles that don't intersect one another, and those are going to be circles that share a common center point. All right, so all three of these circles are going to share a common center point here, and the center point is going to be that center point, that center point, and that center point. And these are called concentric circles. Notice that they still have no point of intersection. They are just within one another and share the same center point. If they don't share the same center point, they're not concentric circles. Like you could easily make something like that. Those are not concentric circles because they have to share the same center point. So real quick, I want to take a deeper look at these tangent circles. And a line or segment that is tangent to two circles is called a common tangent. And so real quick, I want to take a look at identifying some common tangents on some different sets of circles. So here's going to be one set of circles, well, a circle and a square, but there's one set of circles. Here's going to be, my software always makes such nice circles when I'm by myself, and then I try to help you guys out. And it's always bugged out. So there's the second set of circles, and then finally, here is the third set of circles. All right, so let's identify some different tangent points. All right, and on each one of these, we're going to draw the center of the circle, and we're going to draw a segment from there to there. From there to there. Oops, that first one might be a little off. And from there to there. All right, and the reason why we're drawing these segments that go from the center to the center is that we have two different types of common tangents. All right, we can have what's called internal common tangents and external common tangents. A common internal tangent intersects the segment joining the centers of the circle. And an external does not. So real quick, we're going to draw our internal segments with blue, or sorry, our external segments are going to be blue. And our internal tangents are going to be red. All right, so I think it's a little bit easier to visualize our external tangents first. And an external tangent is going to just be something that starts on this circle, touches that one, and touches that one too. I failed miserably at that. So we'll retry. There we go. So that blue line is going to be one tangent line. Notice that it intersects at exactly one point on both. And then we're going to have another tangent line, if I can draw today, right there. So those blue external tangents are pretty easy to see, but the red ones, in my opinion, are a little bit more difficult. So we're going to run from here to here like so, and then we're also going to run from here. I wish I could just swing that top around and just snap it into place, but it's just not wanting to work today. There we go. So these red lines are also common tangent lines because they also share a point there, and a point there, and a point there. But notice they cross internally within the circles, right? They cross between the two circles. They're not on the outside. They also cross this black center line. So those are what common internal tangents are. This specific set of circles, when they're not touching each other, they will have
Charging battery.
Oops. They will have 4 common tangents. All right, now let's see how many common tangents this guy has. So here's one, and then we're going to draw another one right there. All right. So those are 2 blue external tangents, and then we're going to have one common internal tangent. So the 2 blue external, the 1 red internal, and this is going to be 3 common tangents. So 2 circles that touch each other at one point are only going to have 3 common tangents. And then finally, we're going to have the circles that intersect at 2 points. And these guys are only going to have 2 common tangents, and they're both going to be external tangents. There's no way you can draw an internal tangent that would it doesn't work. If you want to try it out, go right ahead. It doesn't work. All right, so this is all the different definitions that we're going to need to know in order to be successful for Chapter 10 material. And we might want to know, though, as well, a couple of theorems along the way. So let's get started with Theorem 10.1. And Theorem 10.1 is going to be the tangent line to circle theorem. And so what this says is a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle. And then, of course, it has to be at its endpoint. So if I draw a circle here, we're going to call this circle Q. And we're going to draw in a radius here, and the endpoint of this radius is going to be called P. And then if we draw a tangent line M, the only way that M can be tangent to this circle Q is if they intersect here perpendicularly. And so line M is tangent to circle Q if and only if line M is perpendicular to the segment PQ, also known as the radius. And then theorem 10.2, which is the more important theorem in my opinion for today anyways. I'd say theorem 10.1 is more used, but theorem 10.2 is going to be called the external tangent congruence theorem. All right, so let's scroll back up here. Notice that on each one of these external tangents, they look almost identical. All these blue segments look almost identical. The only difference is where I messed up in drawing. Other than that, they're just mirrored of one another. And that's what the external tangent congruence theorem is going to state, is that tangent segments form a common external point, or sorry, I misread my own lighting. Tangent segments from a common external point are congruent. So if we draw a circle out here, P, and we put any point out here, we'll call that S, and we draw two segments that are congruent to this circle from point S. All right, so those two blue lines are tangent lines. Since they're both originating from the same point S here, they have to be congruent to one another. Right? You can see that if we were to join these two with a chord, that would form an isosceles triangle. So RS is congruent to ST because of that theorem. So with that information now, we can finally move on to some examples for today. There's lots and lots of definitions that we had to go through. But the examples go by pretty quickly. So I'm going to give you a circle here. Actually, we're probably going to need to move the circle over a little bit. Alrighty. And then we're going to go ahead and draw a center circle here, P. Go there, and then go back there. We're going to have a point here, S, and a point here, T. And we're given the following information. TP is going to be equal to length 12, TS is going to be equal to length 35, and SP is going to be equal to length 37. So how can we verify that ST is tangent to circle P? Well, we just said up here in this first theorem that a tangent line is perpendicular to the radius. And we notice that the radius of this circle is going to be highlighted here in purple. And so for this to be a circle, we need this tangent line, for this to be a tangent line, we need this segment ST to be perpendicular to the radius TP. Well, notice here that now if I highlight this all in this pink color, that we form a triangle right there. And we know that we can test that if this is a right triangle by using the Pythagorean theorem. So we're going to use the Pythagorean theorem to see if triangle PTS is right. And if that is a right triangle, then we know that these intersect at a right angle, and we could call ST a tangent line. So all we need to do is verify that 12 squared plus 35 squared is equal to 37 squared. And if you bust out a calculator, you'll see that that does indeed equal that. So thus, the segment ST is perpendicular to TP, and so this line is perpendicular to the radius, so ST is a tangent segment. All right, pretty straightforward. I'll let you continue looking at that while I jot down the next example. This next example, we're going to have a circle. We're going to call that C, and this circle here, I'm going to highlight both of the radii with R, and then we are going to go ahead and draw a segment out that way, and then this segment is going to continue our line right there. Actually, we're going to continue that line out like so, and like so, and form a triangle. You see what we're doing here? I'm just doing it very poorly. Okay, so we have this triangle here, and this triangle is going to be ABC, and the C point is the center of a circle. We're also given some lengths here. So this blue segment is length 50. This blue segment on the bottom is length 80, and those are both in feet. But we don't know the radius of the circle, and our goal is to find the radius of this circle. And we are given that AB is tangent to circle C. So since we know that AB is tangent to circle C, we also know that this has to intersect at a right angle, because it has to be at a right angle to that radius. And because of this is a right triangle, we can now use the Pythagorean theorem. So we know that segment AB squared plus BC squared is going to equal AC squared. And so AB squared is going to be 80 squared, and then BC squared is going to be R squared, and then AC squared is going to be 50 plus R, the quantity squared. And so 80 squared is 6,400 plus R squared is going to equal 2,500 plus 100R plus R squared. And now if we see that we have a positive R squared on both sides, those are going to cancel out. We're going to subtract 2,500 over to the left side. So we're going to be left with 3,900 is equal to 100R. Or in other words, R is going to be equal to 39 feet. All right, and then finally, I have one last example for you. This one I think might be the simplest example so far. But, you know, you always have to be careful with saying the word simple in mathematics. And so we're going to have circle C here, and then we have an external point out yonder. We're going to draw two tangent lines from this common exterior point, and already you should be thinking that, oh wow, these two segments are going to be congruent to one another, All right, that's theorem 10.2. And we're given that the length of the top segment is 28. The length of the bottom segment is 3x plus 4. And our goal here is to find x. So that's pretty straightforward. We just need to go ahead and set these two quantities equal to each other and solve for x. We know that these two green lines are tangent to the circle. They share a common exterior point, so they must be congruent. So 28 is equal to 3x plus 4, or 24 is equal to 3x, so x must be equal to 6.